Hey there, sports fans. If you're working at calculating area using the limit, stay tuned. Welcome, this is Planet Numeracy. My name is Mark Noldy. I've been teaching high school and college math for almost 25 years now. I know I don't look that old, but let's look at a problem that you'll probably not run into again until the final exam. So we're looking to find the exact area under the curve f of x equals 25 minus x squared on the interval 0 to 5. Okay, that's a closed interval. And we're going to do that using the limit definition. So this is the area, the exact area, if you're using a limit, is this limit as n goes to infinity of the sum as I goes from 1 to n of f of c sub I times delta x sub I. So this is where our c sub I is known to be equal to delta x times I. All right, so we also must now find out the delta x. So delta x, that's our b minus a all over n. So b comes from up here, 5. And the O, which is already underlined, is a 0, or the A, divided by n. So my delta x is 5 over n. So as I go to set this problem up, what I'm going to be looking at is the sum as I goes from 1 to n. Well, let's not forget my limit. N's going to infinity. We're making infinitely many rectangles under the curve. And that curve becomes f of delta x times I times delta x. So let's go ahead and make those replacements. So got to go back up here, look at my curve. I have the limit as n goes to infinity of the sum from I equals 1 to n of, let's see, here is my f of x. So I would have 25 minus delta xi, and this is being squared, and it's times delta x. And what is delta x? Well, delta x is 5 over n, so let's make that substitution. So still the limit as n goes to infinity of the sum I equals 1 to n of 25 minus. So delta x I know is 5 over n, and I, so I'm going to square that and multiply the whole thing by delta x, which again is up here 5 over n. So let's go ahead and do some algebra here. Limit as n goes to infinity of the sum I equals 1 to n. So at this point we need to enter some of the functions that we know. I know that as I goes from 1 to n of a constant, that equals c times n. So I am going to be using that. I started to draw this one in, but we're going to be using that as well. Another summation formula that hopefully you've learned that before you do one of these. So this would be n times n plus 1 times 2n plus 1 all over, scooch that around, all over 6. So this is something I don't necessarily make students like memorize this, but they will learn it over time. They'll eventually be writing it in automatically. So I'm going to go ahead and just simplify some of this stuff before I make my n substitutions. So I have 25 minus, let's see, this would be 25n squared times I squared. So I always write this kind of off to the side because this I squared is going to become this business over here. All right, and then that whole thing gets multiplied by my delta x, which again, up here, that was my 5 over n. So, let's keep on trucking. Now I'm going to use I already have an n here, and whoops, undo that. Meant to point. I already have an n here and an n here. So now I'm going to put n's in place of everything else. And that means I can get rid of this summation symbol. So I'm going to have the limit as n goes to infinity of 25n. And where that's coming from is that's 25 times n. That's this formula right here. Minus 25 over n squared. And then I squared just becomes this here. So I'm going to say, well, that is going to be n times n plus 1 times 2n plus 1 all over 6. And that whole thing is being multiplied by 5 over n. So this is, keep in mind, this is like the length or the height of my rectangle. This is its width, length times width, length times width. So that's why I still have to have this on the outside. But as I start to simplify and distribute this to this term as well as to this term, I see that this is going to become, well, 25. Let me switch colors. This times this becomes 125. The n's will end up canceling. So that just becomes 25. Or we could say, from when we did limits at infinity, so I'll leave limit here for a moment. Limits at infinity, when we had the same the same exponent on top and bottom, it just went to the ratio of the two coefficients, which would be 25 times, oops, I forgot, distribute the 5. 125. So that would be the ratio of the coefficients, 125 to 1. Over here, I would have, well, I'm going to have a 25 times 5, which is 125, over n cubed, times n plus 1, times 2n plus 1, all over 6. All right, so now we have this. So this is now distributed. So all I have to do is use my rules for when I'm evaluating a limit at infinity. So this is going to be the ratio of the two integers, which ends up being 125. So now I can lose this because I'm going and evaluating. And then over here, notice I have an n cubed on the bottom, and I have n times n times n on the top. So I know that my n cubes are going to cancel out. So again, I'm looking at ratio of integers. So I would have 125 times 2 all over 6. So when I evaluate this, I end up with 125 minus, let me touch in my calculator real quick, 250 divided by 6 is, that's 41 2/3. Or in my calculator it says point rapid in 6. So when we subtract those, we end up with 81 1/3. So check the channel out on Friday morning. We're going to look at this problem, which is very similar to what we just looked at. I just changed 25 to 27. But notice my interval does not start at 0. So the process we just looked at is for when the interval starts at 0. It's a little bit more challenging when it starts somewhere else. So tune in Friday morning for that. I hope you like this kind of content. If so, like, subscribe, or comment. As always, don't forget, math is not a spectator sport. In order to learn math, you must do math.